Hi, and welcome to this next video from the differentiation section of the Year 2 course. And in previous videos we mashed our way through all the chain rule stuff, which dealt with a wider range of different functions. What we're going to do now is have a look at a couple of rules that will allow us to do some things in different formats. So what we're going to be doing is looking at something called the product rule, where we're differentiating two functions that multiply together. And then in the next video we'll look at quotient rule, which is the division equivalent. So let's have a look at product rule first of all. Now, chain rule was always a function within a function. So, for example, we might have log x squared plus 1, where you've got an x squared plus 1 sitting within a log function. What you've got here is two completely separate functions, and clearly they're being multiplied together. So I've got one function here, which is my 3x squared, and that's been multiplied by this function here, which is a linear function, that 2x plus 1. Now, for this one, we've got a couple of options. First option might be to say, well, okay, let's have a look at it by doing differentiate the two functions separately and then just multiply them together. That seems like a sensible approach, so let's have a go at doing that. So let's differentiate 3x squared, gives us the 6x, and let's then differentiate the 2x plus 1, that gives us 2, times these two things together, and there's our result. So when you differentiate 3x squared bracket 2x plus 1, you appear to get 12x. The other option we could do would be to multiply out the brackets and then do the differentiating. So almost like a kind of differentiation BODMAS type of deal, if you will. So let's have a look at what happens if we do that. So here we go. So let's multiply out the brackets. That gives us 6x cubed plus 3x squared. And now let's differentiate that. So we end up with 18x squared plus 6x. And straight away, hopefully, you can see we've got some kind of an issue. First thing is that, well, one of those is right, one of those is wrong. And this one down here is the second one that's the correct answer. The first one absolutely isn't. So we've got something going on in here. We've got something that tells us that we can't just do what we did up here and just differentiate the two things separately and add them together. So what's going on? How can we take something that's like this without having to do the multiplying out and end up with an expression or a result that looks like that? Now, it might be you say to me, well, why do we need to bother? Why can't we just multiply out and then do the differentiating? That seems fairly straightforward. Well, the answer to that question is indicated by this example here. So for the first one, this one from the previous slide, that's easy enough to multiply out. But what happens if you wanted to multiply that? That thing there would, it's doable, but it would require a power 8 binomial expansion and then a multiplication by 3x squared and then a differentiation of essentially 9 separate terms. Doable, but a pain in the bum. Having said that, this one here, how do we even begin to think about multiplying that out? The bottom line is you just can't. So we need a way to be able to deal with functions in these styles. So here we go. We need to be able to find the differential or two functions multiplied together, so f of x times by g of x. So let's go for differentiation from first principle. And our standard result for the differential of f of x is f of x plus h minus f of x over x plus h minus x, or as our limit of h tending to 0. This one over here is just the bottom bit tidied up. And so if we apply that principle to this expression here, what I'm going to do is take my function f of x g of x and replace that with f of x plus h g of x plus h, and then I'm going to subtract f of x g of x. So what we get is that. So just take a moment to make sure you're happy with what I've done then, that's just basically our basic setup for differentiation from first principles. Now, it doesn't look like there's a whole lot we can do with that, so I'm going to do a little bit of sneaky manipulating it. And again, don't worry, the purpose of this is just to show you where product rule comes from. You're not going to have to be able to reproduce this in the exam. So bear with me, here we go, here's our sneaky trick. What I've done is taken exactly the same thing we had from the previous slide and just written it with a massive gap in the middle. Because this bit here, that's our f of x plus h g of x plus h, there's the subtraction. And I've left that gap because what I'm going to do is I'm going to include some extra terms. And the first term I'm going to include is a subtraction of g of x, f of x plus h. And you might go, well, why the hell are you doing that? Well, bear with me, it will hopefully become obvious. But if I'm going to make sure that this expression here stays exactly the same, if I've subtracted that on the numerator, then I've got to add the same term back in. So this red bit here is sums to 0. So I haven't changed it. And you're thinking, what the heck is he doing? Well, again, I keep saying, bear with me, it will all become clear. That is the same expression just written out without the red bits. And so now what I'm doing is looking at this and saying, these first two terms, if you have a look at this term here and also this term here, they both contain f of x plus h. And in the third and the fourth terms, I've got g of x appearing as a common factor in those two terms. So what I'm going to do is factorise. I'm going to factorise the first two terms across with f of x plus h, and terms 3 and 4 I'm going to factorise across with g of x. So what we get is that. So again, just keeping around the brackets, you'll notice I've got a bracket around this g of x plus h minus g of x. So that's taking f of x plus h out of there, and the same thing's going on over here. The next thing I'm going to do is write it just as two separate fractions. So I've split up, so this bit here is my first fraction, all over h, and this bit here is my second fraction, all over h. And if you look carefully at what's going on, let's just have a look at this first fraction. You have a look at that section there. That bit is just basically g of x plus h minus g of x all over h. Compare it to the bit that's now highlighted at the top here. We can see that is the differential of g of x. And the same thing is happening over here. If I just highlight those bits there, that bit is the differential of f of x. So all of a sudden this thing's going to become a whole lot more simple if I just replace those highlighted bits with the red bit, g of dash x, and the blue bit, f dash x. And now we appear to be making a bit of progress. The last thing we've got to do is say, well, we've got this f of x plus h. As h tends to 0, that gives us f of x plus h will just tend to f of x. So now I've got my result which says when I differentiate the products, I end up with f of x times by g dash x plus g of x times by f dash of x. Now, that looks like an absolute mess. You're probably looking at this slide and thinking what an absolute horror show of brackets and functions that is. As I said before, you don't have to be able to reproduce all of this. You just need to know how to use this rule here. And again, this actually breaks down into something really, really simple. If you look at it, what we've got is leave the first expression alone. So this one here, I've got f of x, and then just multiply it by the second product differentiated. That's the first bit. And then I've got to add on what I get from leaving the second one alone, g of x alone, and differentiate f of x. And because it's an addition, it doesn't really matter which order you do those in. So it breaks down into quite a nice, simple, neat, leave the first one alone, differentiate the second, leave the second one alone, differentiate the first. Right, so let's have a look at the example we had from the first slide and see now if our product rule will now give us the result we got from multiplying out. So when we multiplied it out, we knew that when you differentiate it, here, differentiate, multiply this out, differentiate it, that's the result I get. Using the product rule, let's see what happens. So here we go. So what I'm going to do is f of x is the 3x squared, g of x is the 2x plus 1. And if I have a look at my product rule, it says I've got to leave the first one alone, differentiate the second, plus leave the second one alone, differentiate the first. I've got to be honest, when I do them, I do it the other way around. I said on the previous slide, it doesn't matter which way around you do it. I've just written it in this version up here because that's the result that popped out from all our workings from the previous slide. But what I'm going to do is I'm going to differentiate the first one, leave the second one alone. There we go. And now add on to that what I get from differentiating the second one. So just differentiate 2x plus 1, I get 2. Leave the first one alone. There it is. So there we go. There's my result. What we're going to do now is prove that this thing here, when we tidy it up, ends up as 18x squared plus 6x. So let's multiply the brackets, do a bit of tidying up, and there you go. The two things are exactly the same. So our product rule is working. So there we go. Nice one. Right. Let's crack on and have a look at the other two examples that I mentioned previously when we talked about this one that would, if we multiplied out, would require a massive binomial expansion. Let's ignore the binomial expansion thing and let's do it using product rule. So here we go. So differentiate 3x squared, leave 2x plus 1 to the power 8 as it is. And then I'm going to leave 3x squared alone and differentiate 2x plus 1 to the power 8. So that thing is going to be a chain rule by inspection type of deal. So take a second and say, well, we've got to bring the power to the front, we've got to bring a 2 out of the bracket, knock 1 off the power. That's what we end up with. So again, quite often you will end up with a chain rule type of an issue sitting inside a product rule. So all we've got to do now is a bit of tidying up. And what I've done here is notice, well, if you have a look, you've got two terms. You've got this section here plus this one here. and the common factor is 2x plus 1 to the power 7. So what we know, we've got 2x plus 1 to the power 7. From this term here, I've got 6x times by 2x plus 1. And from over here, we've just got the 3x squared times 8 times 2, which is the 48x squared. All that leaves me to do now is tidy up what's going on inside the brackets. I'm going to do that by multiplying out there and collecting terms together. There we go, and we can see straight away inside that bracket now I can do a bit more factorising, so I can take a 6x out of there. And so we've got 6x times by 2x plus 1 plus 7 times by 10x plus 1, and there you go. Now, it depends what you're being asked to do in the question. If you're just being asked to differentiate and then, for example, just find a gradient, it might be you can just deal with this thing here and just put a value of x into that and it'll pop out a number. If you're being asked to work towards a specific result, it might be you've got to do this extra factorising work. So you don't need to do these last kind of 3 steps here unless you're specifically being asked for it. So just think carefully about what you're being asked for in the question. Think about what work you need to do and what work you can avoid if you need to. Right, on we go. Differentiating this one. So same thing. Here we go. So let's differentiate x squared, leave the sine x alone, and now we'll leave the x squared alone and differentiate sine x. There we go. And then if we need to, just a tiny bit of factorising that we can do there, take out an x, and we end up with x bracket 2 sine x plus x cos x. And there you go. There's your differentiated version of that product. Right, okay, last thing we're going to do is have a look at something that is, this one to be quite honest, is a bit of a shocker, but we'll crack on through it, and this will be a whole product rule type of deal and putting it into the context of finding a turning point. So, here we go. Given y equals sec x, find dy dx. Now, you'll notice in your formula booklet there's a whole bunch of trig functions that you're given as standard results. You might on occasion be asked to prove 1 or 2 of them depending on whether or not they require a product rule or a quotient rule or something like that. So it's not beyond the realms of possibility to be asked to prove them, but in most cases you can just look them up in your formula booklet. So what we're going to do here, we're going to find dy dx, we're going to differentiate sec. And what we're going to do that is we're going to write sec as 1 over cos x, which is cos x to the power minus 1. I've put a note there saying that that's not the same as cos to the minus 1 of x, because that thing here is the inverse function. This one here is the reciprocal function. So those two things are absolutely not the same. So here we go. What we're going to do is do some differentiating on that initially. And this one's going to be a chain rule one to begin with. The product rule stuff is going to come in the second part. So let's do a chain rule by inspection. So it's bring the power to the front, differentiate the function itself. So differentiate cos, I get minus sine, and then take 1 off the power of the original function. And we end up with that. So we've got here minus 1 times minus sine, that makes that positive, and then I've got over cos squared x, and there we go. Now, a little bit of tidying up there, we can write this as sine x over cos x times by 1 over cos x, and we know sine x over cos x is tan, and 1 over cos x is sec. So as it turns out, differentiate sec, you get tan x sec x. And like I said, that result is in the formula booklet, but there it is. That you're kind of being able to prove that is not beyond the realms of what you might be expected to do in the exam. Okay, so that's dy dx. Now let's go for d squared y over dx squared, and hopefully now you can see, because we've got tan x sec x, we've got a product here. This is where our product rule is going to come in. So here we go. Differentiate tan, and we know from differentiating tan we get sec squared, and again that's a result that is in the formula booklet. And then leave the sec alone. There it is, that's the first bit done. And now what we're going to do is differentiate sec, so differentiate the second one, which we know differentiate sec is tan sec, that's the result we just proved, and leave the tan alone. So we're there, and what we've got now is sec cubed x plus sec x tan squared x. Now the result we're aiming for just contains sec, so we need to get rid of the tan. So we're going to have to replace the tan squared, and we're going to do a little bit of scribbling. So, well, let's go back to our sine squared plus cos squared equals 1. We need to replace tan squared, so tan is sine over, so let's just do the dividing by cos squared. So what we've got here is tan squared plus 1 equals sec squared, which therefore gives us sec cubed x plus sec x, and there's replacement. So tan squared is sec squared minus 1, and then the multiplying out. And there we go, you can see we're going to end up with the result that we're after, because we're going to get an extra sec cubed coming from here. That gives us 2 secs cubed minus the sec x. And there we go. Right, so that's part A done. So as with a lot of exam style questions, I'll ask you to do a bit of working in the first part and then ask you to use it in the second part. So on we go to part B. So we've got the curve y equals e to the 2x sec x, and it's got a turn point, and we're looking at values of x between minus pi over 2 and pi over 2, and we need to find essentially the minimum point. So here we go. Again, you can see we've got a product rule going on, because what we've got is that function there multiplied by this one here. So let's do that. So let's differentiate e to the 2x to e to the 2x, leave the sec x alone, and then differentiate sec. We had that from the previous slide. There it is, sec tan multiplied by the e to the 2x left alone. So that's our product rule. Now what we've got to do now is just do a little bit of tidying up. So I've taken out e to the 2x sec x. The reason I've done that is because we're going to be finding a minimum. We've got to put it equal to 0. So when things are equal to 0, life's a whole lot more simple when you've got everything written as a product. And in this particular case, I've got 3 things multiplying together: e to the 2x times by sec x times by 2 plus tan x. So what we're saying is either that one is equal to 0, or that one is equal to 0, or that one is equal to 0. So potentially we've got 3 solutions coming from here. But as it turns out, we absolutely haven't, because if you think about it, if we look at that, we say, well, e to the 2x, that can never be 0. Sec x, that can never be 0. So the only way that we're going to get a solution is if it's the 2 plus tan x equals 0. So therefore, x is tan to the minus 1 of minus 2. And so we've got, in radians, our value of minus 1.107, and that's between our required limits of minus pi over 2 and pi over 2. Right, so that's our value for p. So we need to get our y value, which is our value that's q. So I'm just going to plug my minus 1.1007 back into the original equation. And it's just a case of chuck it back into the calculator, and you might need to be using 1 over cos on your calculator instead of sec. And we end up with a y value. So there we go. There's my 2 values for p and q. That one was reasonably okay, but it's the next bit where it's going to go a little bit bonkers, because we need to determine whether it's a maximum or a minimum, which means we're going to need the second differential. So we're going to have the second differential of this thing here, and what you've got is you've got a product going on in this term here, so we've got a product rule happening here. We've also got a product rule happening here, and you're looking at this again, well, we've got 3 things multiplied together: e to the 2x, sec x, tan x. But if you remember, we already had the result that d squared y over dx squared equals that, which came from dy dx there, so that's going to make that a little bit easier. Hopefully you're keeping up with this. And so off we go. Let's do some differentiating. So let's do a product rule on this first bit here, just the bit I've underlined it in red so we can see what's going on. So differentiate the first bit, leave the sec x alone, leave the 2e to the 2x alone, differentiate sec, which we know is sec tan. So that bit there is product rule applied to the bit that's underlined in red. And let's add on to that what we get from differentiating this bit here. So again, I've got my differential of e to the 2x plus leave sec tan alone. And now let's leave the e to the 2x alone and differentiate sec tan. And we know from differentiating sec tan, the result we got was this bit up here. So let's plop that in. Oh, there it is, appeared on the slide. So there we go. So we've got that. Now, again, at this point, it depends what you're being asked to do with it. I'm kind of just by default started tidying this up, and then after I wrote the PowerPoint, realised I could just plot my values of x into here. But let's just do a little bit of tidying. I mean, you could just put your x value minus 1.107 into all this bit. It's just a case of typing it all into the calculator, which is entirely doable. I'm just going to go down the route of simplifying it, just because, like I say, I'm a little bit OCD and I like things nice and neat and tidy, but technically I don't need to here. So let's see what we've got common factor wise. Well, first thing that I've got to do is tidy up that bit there, and then mention common factors. So we've got 4e to the 2x sec x, so because it's there, it's in there, and we've got an e to the 2x, and we've got sec x in both those bits. So let's see, so that bit there is 1. This bit here, plus tan x. This bit here, I've got 2e to the 2x, I've taken out 4, so I'm going to need a half sec squared x there. And from this last term here, which is e to the 2x times by minus sec x, so that's going to be minus a quarter. So again, that would be the tidied up version of it. And then let's just put our value of p is, our value of x, which is minus 1.107, into all of that. And so our value is, for c squared y over dx squared, 1.211. Bottom line is I don't much care what it is, I need to know whether it's maximum or minimum. That thing is positive, so there's our statement. D squared y over dx squared is greater than 0, therefore it's a maximum, and there you go, we've answered the question.